Hey, Rob.
Hey, Betty, glad to see you could join.
Yeah, thanks, Rob. How are you?
I am just fine, thank you.
Good, good. I have some questions for you, so maybe later, or I'll send you an email.
Okay. I don't know if I'll have the answers.
Well, you could try.
I always try.
That's good.
This
All right.
event is being recorded. I hope that it's successful. There were some problems from recording yesterday's meeting, even though it said it was recorded. So I'm not quite sure what the situation was, but
Oh, okay. Well, I hope people are gonna join. Can you
I
make
hope
me
so.
as co-host if you don't, or I mean, if you're staying around, that's fine.
My meeting, this timing actually worked out better for me personally, so I will stay on for the duration of the call till
Perfect.
11 o'clock Pacific. I see we have 8 total participants.
Yep.
6 attendees. Very good.
All right.
Hello, Kevin. Vladik, hello.
Hello, good morning. This is Władek Grawiński speaking. Can
Eric,
you
hello.
make the list of the participants available to all?
I'm sorry, ask the question again, please.
Can you make the list of participants available to all? In my Zoom window, it's disabled, so I cannot see who is joining.
All right, let me see if I can do that. I am a comparative Zoom novice, so forgive me for that. Eric, welcome.
Hello, how's it going?
Going well, thank you.
I noticed the chat is also disabled. Sorry.
Yes, yes. Chat is disabled, and I cannot see the list of the participants as it's kind of open meeting. It would be great to see all who are joining us. So I was distributing. Yes.
Let me, you should have been added, you should have been listed as panelists, but apparently that's not the case. Only Mehdi and I are showing as panelists, which obviously is not the desired effect. Let me see.
Okay, it's not really critical.
I got it. Let me, I am promoting you to guys to panelists. I apologize for the problem. So I have I'm going from memory here. So Vladik, Mehdi, Eric, you are all now panelists. And I think who else was Sergey supposed to be a panelist? I forget.
The list is so Macris from NG Spice.
Oh, Marcus. Okay.
Macris.
Macros.
Yeah.
Sorry.
And Tim Edwards. I don't think he's around, but
Tim
he said,
hasn't joined yet.
yeah, he said he's going to join later. I think some of them are going to join later because they have other things to do.
Okay. All right. So yeah, so just from a procedural perspective, all I have to do is just promote folks to the panelist level. That should have been taken care of in the original invitation. I don't know why that was not the case. But certainly let me know if anything needs to be repaired, but hopefully.
So I seem to be a panelist now. I'm guessing the reason I wasn't a panelist before might have had to do with me switching email addresses from my Sandia account to my Gmail.
Yeah, Eric,
Possible.
I don't know, because
Yeah.
certainly Vladik was always listed as a panelist, and so were some of the others. So I really don't know why there are some of these discrepancies with Zoom, so to speak. But thankfully, able to revise these here on the fly. So that's good news.
Yeah.
And I want to thank all the panelists for making time to come today, and also for the audience for, I think, what will be a very informative session. So I'll put myself on mute and let you folks take over.
What's our format here?
Mehdi or Vladik, you want to take the lead on who goes first, or what the order,
Yeah, so
So-
Vladik, do you want to lead that, please?
So good morning to all, and I'm really glad seeing outstanding lineup of panelists today, and growing list of attendees. I'm sure it will be very informative discussion and presentation about modeling, simulation, and IC design, in particular using open source free PDK from Skywater. And I guess there was a request to slightly change agenda, and I think, did you, Kevin, ask to be first because of your time?
I need to go before 10 o'clock.
Okay, so
Yeah,
if
I was just going to
you
take like 10
already,
minutes though.
maybe we can start with your talk. It's an update on standardization efforts, and I'm sure this will be of your interest, and then we will return to the presentation as we schedule. So let's begin with first presentation by Kevin on his contribution to IEEE standardization efforts.
Yeah, I was just going to do a quick rundown of what standards are running and what the opportunities are. So I don't know if I'm speaker, it should just show my list of stuff in the background I can talk about.
Yes, that's what we're seeing.
Yeah. So my background in this is I started somewhere in the 80s on a standard called, I think it was ALVI 042 in the UK, on mixed signal simulation, which I wrote a very thin paper for that the government didn't think was thick enough. I moved on from that and into Verilog AMS in the 90s. And in the 90s, there was Cadence and who was it? Analogy were trying to standardize what they had in languages, and Cadence's Spectre stuff became Verilog A essentially, and the other effort became VHDLA. I'm not really sure if anybody uses VHDLA, but it's still there and has the advantage of being an IEEE open standard, so anybody can participate in VHDL stuff if they want it, the IEEE. Verilog AMS should have combined with Verilog and gone to the IEEE. What happened was that the system Verilog guys came in, that was actually Superlog at Accelera, and they sort of forced their way through to IEEE without incorporating Verilog AMS, and Cadence were dragging their feet on the thing. So system Verilog ended up at IEEE, and Verilog AMS kind of got abandoned at Accelera, and it sort of ran along till, you know, somewhere around 2014 or something, where there was a sort of a final version with some broken stuff in it. I think that was the last official Verilog AMS effort. What's happening at the moment is that people who are doing UVM AMS and System C AMS are looking for ways to interact with System Verilog. So System Verilog arrived at the same level as VHDL with user-defined types a few years ago, but has the same problem as VHDL, that they have not been able to work out how to get multiple types on a net. And getting multiple types on a net is where the mixed signal stuff comes in. So we've already done multiple types on net with only 2 types, logic and analog, in Verilog AMS. So what I'm currently working on is trying to get the Verilog AMS stuff brought into System Verilog and make that work for any kind of types on a net. The problem there is usually the System Verilog standard is entity only, so it's mostly the EDA vendors playing there, and they don't actually like changing their software much. So basically, you need to pack the committees with people who are interested in actually having it work in order to get things through the IEEE committee there. Mentor Graphics, now Siemens are the people pushing this, and it's mostly from the UVM AMS end, I think. But a lot of the stuff in the AMS space is being done in Accelera, and Accelera is pretty much a closed shop where I can't really see what's going on because I'm not a member at the moment. So the stuff in System Verilog that we're trying to do right now, and this has only been going for like 3 months because they decided they would do us an emergency push to try and get things through before they go out next year with the next LRM. So if anybody wants to get mixed signal going, where we can do things with like DPI, VPI, PLI, where we get out of System Verilog into things like Zeiss and NG, Spice, and other analog simulators. What we're doing is basically trying to create hooks at the moment in System Verilog so that you can do these user-defined types, and then the user-defined type can be like a PWL type from an analog simulator if you want. The main reason I work in these standards efforts is that if we can take everybody's little piece and make them all work together, we can build some interesting things. If everybody just works in their corners doing their own special simulators, it's very difficult to get them all to work together and build bigger things. That's some of the opportunity. The P2427 standard is interesting because we're trying to do analog defect analysis. And I think the proposal I put in for this one is that we would do stuff with Verilog A models. So it sort of fits in the ADMS space, where we would just list defects for a device model in with the model definition, and then you could create broken models at the same time as you had working models, and then the simulator should be able to switch between broken and working models as it goes because they have the same footprint and code. So there's an opportunity in there, but that committee is not going anywhere particular. It's set off in sort of the wrong direction and is not adjusting. But we could actually fix that one in open source space and then bring it back in as a phase 2 P2427 thing if people want to do that. P1687.2 was started by the same people as 2427. It's about doing stuff in analog test. One of the things about analog is, unlike digital, you really need to simulate it to see if it's going to work. So there's an opportunity in simulating testers and running your test languages on the simulation to see how things go. And again, the easy sort of entry point for this stuff is sort of ADMS, which is common to everybody, and this is where the modeling stuff's coming in. I'd say in the opportunities, this works for me. Things I think people are interested in is how do we apply AI to EDA stuff, and I'm looking at like a lot of the mixed signal stuff I see, the math and the event-driven stuff looks like neural networks. So I'm looking at a lot of people building AI accelerators, which are basically neural network math machines, which could equally well work as mixed signals simulation machines if you know how to build the models. And then there's automatic ways in AI to build models. So I'm feeling that's something that fits in with what Zeiss does. I'm not sure about the other analog simulators. There's a whole bunch of people trying to do Python-based DV. I feel that the Python and the AI and the analog simulation can all fit together in one thing if people want to go for that. straight up opportunities in EDA. The AMS RF field is kind of broken and open for grabs. And my view is if you want to do mixed signal simulation and open source stuff, you want to go for the weak piece of the EDA market, which is definitely AMS RF stuff. Other standards opportunities, the Open Compute project guys are working on chiplet system design. And one of the problems there is it's multi-vendor, so you can't just use Cadence tools or Synopsys tools or Mentor tools, and that creates an opportunity for doing sort of large-scale open source stuff. So I'm looking at, can we build multi-simulator systems for developing chiplet systems and optimizing them, and get people like Facebook and Microsoft to back that effort. Anyway, that was one where we're trying to do hardware, software co-design and with AI at OCP and the chiplet stuff and high performance compute if anybody wants to hop in there and join the effort. What I would like to get to with that stuff is to be able to do asynchronous logic rather than RTL. That again requires mixed signal simulators rather than the discrete simulators. And then can we get above the RTL level and design at the neural network level, sort of asynchronous FSM? So that's a quick summary of where I'm at. So if anybody's got any questions, go for that.
I should just add, chat has been enabled for all participants and panelists, so you should be able to put them into the chat spot for the panelists to see.
Yeah, it's working.
Very good.
Yes, it works. So please continue.
Yeah, I would say that the proposal I've got in at the system Verilog thing at the moment is that when you're trying to do parallel processing simulation, the thing that you want to communicate between the simulators, whether they're the same simulator or different simulators, is drivers, not signal values. So the mistake people have made in the past is you resolve a value within your simulator and you try and communicate it to other PCs. With something like System Verilog, what we're saying is we got lots of drivers and we got lots of receivers for the signals. You communicate out the drivers, and you also communicate out scheduled values and drivers, and that way you can get some acceleration in the simulation. So none of the EDA vendors do that stuff. So I think there's an opportunity for sort of high performance computing simulation stuff with open source that's fairly easy to get at. Part of my proposal for System Verilog is just a sort of high level methodology for doing things, and maybe interested in sort of filling in an API that will work for like NG, Spice, Zeiss, whatever is Verilog, whatever else is out there. I can't hear anybody.
There is a question from Eric.
Yeah. Yeah. So yeah. So the way this thing, the proposal I've got at the moment is that if you look at how the simulators work, they've got drivers for nets and then there's receivers. And I did a thing for Zeiss where I was pulling out piecewise linear signals and feeding them into the digital simulator and back. And the sort of picture you want is that for all the simulators involved, there's a driver with a waveform, and the waveform is kind of your PWL thing, and there's a receiver somewhere else with the waveform, and you're trying to sort of get values from one to the other. And within the System Verilog environment, we're trying to get it so we can do driver access like Verilog AMS, so you can see that waveform, and then you can use VPI or PLI or DPI to get it out into your analog simulator. I've done a couple of integrations with digital simulators and Spice simulators in the past, so it's really not that hard. It just fits in with the PWL source stuff, and that's part of the proposal to System Verilog, because they're trying to get to UVM AMS and they're trying to get to System C AMS. So they might go for supporting whatever whatever I'm trying to do in some way. If anybody is an entity company member of IEEE, if you turn up for like 4 meetings, you get to vote on things. The only downside at the moment is on the system parallel committee, they might send you a bill for the LRM editor.
Okay. Well, part of why I asked about VPI is I know we've supported the VPI interface in Zeiss, so just curious how this was related to that. So.
Yeah, I mean, the idea here is that if you know the Connect module stuff in Verilog AMS, I invented that like in '95. So basically what we're trying to do at the moment is say, okay, let's just do Connect modules in some form in System Verilog. And a Connect module is basically just a module. So anything you can do in a module, you should be able to do in a Connect module, which means VPI, PLI, DPI kind of access. And the other thing is like we're trying to do this stuff as static structures where everything's sort of laid out at elaboration time, so you can optimize it and make it go fast. I think one of the things though with Zeiss is it'd be nice if we could do stuff where we can hack at the circuit as we go. So there's some ability to do restart, and that's where the P2427 stuff comes in. If we can do the defect, and there's a sort of market for this defect analysis and coverage stuff. And if we could get Zeiss to do that, then we'd probably have quite. And it's not hard to do that one because I think you can probably switch models while you're running.
Yeah, I'll talk about that a bit in my talk, I guess.
Yeah.
So.
But P2427 is a good opportunity, and also the 1687.2 stuff. It's just those committees need better direction, but there's definitely powers there that you can leverage and say, okay, we can make our tools do this, and we can also start our own powers at IEEE for doing things and just create our own standards. My feeling at the moment is if the system Verilog AMS stuff doesn't fly, we just go for doing a new power and do a standard for how to mix simulators together, do it all as an API thing. But that requires like signing up at least a dozen people to get a committee going.
Right. Okay, thanks.
Cheers.
There is one more question in the chat.
Yeah, let me see. Yeah, so if you know how the simulators work, Eric can probably talk about this more. SPICE simulators are a large matrix math thing. A fast SPICE simulator tends to be small matrix math pieces, which are the hard pieces, and then lots of event-driven stuff between those. So something like what we're shooting for with Verilog EMS is you have accurate models of analog things, event-driven models of digital things, and you're mixing those together. That looks a lot like a neural network. You got layers which pass messages between, and then there's matrix math. So in my mind, Verilog EMS would be a perfectly good language for describing a neural network. You're doing a shorthand for the math in there. Circuits don't really need a lot of precision in the models, which is like neural network stuff. They're always trying to cut down the size of the math. What that means is if you've got a platform that can do fast SPICE type simulation or mixed signal, it should be able to do neural networks as well. So there's a sort of common sort of computing level for mixed signal simulation and neural networks, and that means it's probably easy to mash a neural network description of a circuit with a simulation of a circuit, and then you can optimize and use AI to design circuits for you. RTL level is just the wrong level to work at for a lot of things. So if we can just sort of bump up a little bit to this kind of neural network level, then a lot of things become easier. And that's why it's interesting to say, let's pull in Python as like a way of driving Zeiss, and then we can pull in all this AI stuff as well. I don't know if that clears up anything for now.
So I will comment that there's a whole field of research in physics informed neural nets, and people attempt to discover models from data, and a lot of, depending on what sort of activation functions you use and stuff like that, neural nets can often resemble a discretized differential equation. And so we've done a bit of research in that area. My talk's not really about that, but we've had a couple projects at Sandia where essentially we often have some weird physics we need to model, and it takes forever for the physicists to figure out a model for it. But we have data. And so if we can just sort of take the data and then apply some data-driven technique like neural nets to it and create a model quickly, that's a big win.
Yeah,
So that's the area of research.
Yeah. If you ask me later, I know somebody who says they got a one-shot approach to that kind of thing. So rather than going round and round trying to do your gradient descent optimization, they say they can do it one pass off the data. So
Okay,
that might work for you.
That sounds cool.
So somebody said, it sort of works, but it's not quite as good. But I'm thinking, one pass, it's a good start.
Right. Okay.
So,
well, it could be interesting.
Yeah, I'll connect you with the guys.
Okay. But yeah, my talk's not really about that, but I do have a blurb about. Zeiss can call Python models that are written to use TensorFlow or PyTorch or whatever.
Yeah, that's the kind of thing. I mean, we could go to the IEEE and create a new standard in there for doing this kind of stuff in some formal way. But it's usually better if you've got something working and you just drop it on the IEEE. And say, it's harder for people to argue with something that works.
Right.
I think you should probably just launch into your talk then. If
well, I don't want to totally mess up the order that was planned. I don't know.
Okay.
I'll leave that to the moderator to choose.
Well, I'll pass on to the next person if nobody's got more questions.
Very well, thank you very much. We'll be looking forward to update. I guess it's quite a long timeline to complete all the standardization efforts. So shall we return to the agenda as we plan, or Eric's talk would be kind of complementary to the presentation just before?
Yeah, I'm fine with Eric starting.
Yeah, well, I should say my talk's not primarily about the AI stuff. So even though that's what I was talking about, but I'm happy to go next. That'd be fine.
Okay, so let's invite Eric, and he will give an update on Zeiss simulator and discussing support of commercial libraries and syntaxes like HSpice or Spectre. I guess the talk will go beyond all these points. So welcome to Eric, and let's start the talk.
Figure out how to share my screen. Oh, here it is. Okay. Hold on a second here. Okay, is my screen visible?
Not yet, but it should show up soon.
Okay, hopefully, let me know when it's there.
Oh, it's up.
Okay,
at least for me.
So sounds good. So I have 2 little slides here, and I threw this together fairly fast. So hopefully this is coherent. Mostly what I'm going to be talking about is our simulator Zeiss and the extent to which we do or don't support modern process design kit. So, just to set some context, I'll give a little bit of an overview about Zeiss in general. I'm going to talk a little bit about Zeiss's parallelism in that overview. The talk is not about parallel solvers, but we tried to put as much parallelism into our parser as possible. And so that sort of impacts the parser design and some aspects of the setup. Let's see, so but a lot of this talk will be about PDK compatibility. And in practice, what that generally means is, if you're working with a commercial foundry, they will have a set of process design kit files that contain all of the IP. And in a small subset of those files will be related to SPICE. And generally, because those foundries have contracts with the commercial EDA vendors, they've basically created a set of files that are, for one of the two common commercial simulators. And the main two are HSPICE and Spectre. And so, for another simulator to be compatible with a PDK, that means that you really need to be compatible with the netlist languages of at least one or possibly both of those commercial simulators. And so that actually implies lots of things. You have to have all of the right device models available. You have to have all of the right analysis types available that somebody might want to use. You have to have good expression support. You have to support the same syntax. Hopefully, some of these modern PDKs are really complicated, so you need to have a parser that performs pretty well and can digest the massive number of files that a PDK might have and do it fairly quickly. So I'll be talking about all of that to the extent that I have time, and I'll give a little bit about what Zeiss's current status is. The big question is that machines compatible with these things is a fairly important priority for us now, although it hasn't always been. So as some of you may be familiar with Zeiss, we started writing Zeiss a little over 20 years ago. At the time, most of us were not originally from the EDA world. Most of us were from fields like plasma physics. So I think there were some things we did very well and some things we didn't do so well. But one of our big focuses at the time was to make Zeiss be distributed memory parallel and to make it work well in parallel. And at least back then, that was kind of unusual. Not that the commercial tools mostly were not parallel, and most of the open source tools weren't either. So we really focused a lot on unique solver algorithms and stuff like that. We didn't focus that much on tool compatibility, which is something I kind of regret. But we've worked a lot on it more recently. One sort of intermediate thing that we worked on is a netlist translator that we call XDM, and I'll talk about that a little bit later. Another thing that's new to Zeiss that we were just discussing in the last talk is we have a Python model interface, which allows people to develop ML-based models, using TensorFlow or PyTorch or whatever library they want in Python, and then to actually execute those models in a Zeiss netlist and just call them from there. So we've had some projects at Sandia, like I said, where we'll get some weird exotic physics that we have to model, and it takes people several years to figure the physics out sufficiently to do a physics-based model. And so somebody had the bright idea, well, gee, maybe we could use a data-based method to develop models using ML. So we have a few ongoing research projects on that topic. The other things about Zeiss, we've been open source since 2013. Starting with Zeiss 6.0, we're under the GPL version 3 license. Our most recent release was 7.6, and that happened last month, November. And we're trying to do releases every 6 months. But also, if people are impatient and they want to get code changes that happen in between releases, we're also up on GitHub. So you get it's not quite our development branch, but we synchronize our internal development branch with the public GitHub about every 3 weeks. So you can get hot fixes that way. So like most SPICE simulators, we support a lot of the standard analysis types, DC, transient noise, AC, etc. There's a number of slightly more exotic methods we also support, like harmonic balance and adjoint sensitivities and polynomial chaos methods. Those I think are a little more unusual, at least in the open source domain. But most of the sort of standard techniques are what people who are running PDKs would want to use. So we do have support for those. I'm going to say a little bit about Zeiss's parallelism, and mostly to sort of set some context for some of the parsing discussion. So there's sort of 3 parts of the problem. So on the right-hand side, you have a flowchart showing what a transient simulation of Zeiss would do, or any simulator would do. There's sort of a nested set of solvers. So there's a time integration loop, and there's a nonlinear solver inside of that loop, and then there's a linear solver inside of that loop. And before all that happens, you have to set up the problem, and that's where netlist parsing comes in. And so I think for a long time, we really only focused on optimizing the device evaluation and the linear solve parts of the problem. And those are the 2 boxes inside of the loop there. but we've also seen performance issues in parsing, so we've attempted to parallelize that as much as we possibly can. And actually, the parallelism that we apply to device evaluation actually starts during parsing, because the essentially, well, I'll get to this in the next slide, but basically, we try to distribute devices before they're even fully set up, and then allow as much of the setup to happen on all the individual processors as possible. So let's see. So in Zeiss's design, we have two different parallel distributions. The parallel distribution for the linear solver is completely separate from the parallel distribution for device evaluation. The one for the linear solve depends very much on the graph structure of the circuit, and so we rely on graph partitioners to try and set that up. But for devices, we don't really have to we don't have to worry nearly as much about the connectivity for the device evaluation, because there's very little communication that's really necessary for device evaluation. And so in the initial design of Zeiss, we just sort of did a first come, first serve type of parallelism for the devices, where if you have 1 million devices and 10 processors, then each processor would get a chunk of 100,000 devices or something like that. And so initially we did sort of first come, first serve. There's other load balances we've applied subsequently, where we try to weight devices based on how expensive they are. So we also can do device weighting. But all of that is sort of determined actually during parsing, because we don't even want to set the devices up before they're communicated. We just want to send tokens describing the device to each processor, and so that's where the parsing comes in. So this is a slide I'm going to revisit a little bit later, but Zeiss's parser design, like most parsers, there is a lexing and a parsing phase, and some of the parallelism happens in between those two phases. There's also multiple passes of the net list. So the first pass of the net list, it's basically lexing and parsing things that don't really have a parallel distribution. So either stuff that's needed only on proc 0 or stuff that's needed on every processor. And then we're also gathering statistics on that pass to help figure out how to do the parallel distribution on the second pass. And so on the second pass, and basically, we know how many devices there are going to be, and we know how we want to distribute them. And so on that pass, then we just do some sort of minimal lexing, and then we pass the tokens around to all of the different processors. And then after the tokens arrive at the different processors, then the rest of the parsing happens and the rest of the device setup happens. So partly for this reason, it's been because the parallelism is kind of embedded in it. That's made sort of refactoring the parser kind of difficult. The other thing is that when we first wrote this, I don't think any of us were particularly familiar with modern parsing techniques. So the lexing and the parsing are entirely handwritten and are kind of clunky. So what we're going to do in the near future is replace the lexing and parsing phases with a much more modern style lexing and parsing. And that should enable us to apply different grammars a lot more easily. So I'm going to revisit this in a minute, but that's basically the general idea. So here's kind of a high-level slide about Zeiss's compatibility. So as I mentioned before, PDK compatibility generally means netlist compatibility with commercial simulators. So we've kind of taken a two-pronged approach to that. One is to continue hacking on the existing parser to get it as close as possible to HSpice, because Zeiss's syntax is not too different than HSpice. And we have a command line option that sort of enables all of the HSpice related syntax that we can, that's available. The other approach has been to do something more comprehensive. We want to, like I mentioned before, we want to replace the lexing and parsing phases in Zeiss with something more modern. And we decided to develop this in a standalone tool first. And so we've been developing a code called the Zeiss data model, or XDM. And that one actually uses a more modern parser generator. It uses the Boost Spirit parser generator. And so we have grammars worked out for several different file formats now. Right now, it's a standalone tool, which basically converts netlists and PDKs from whatever format they're in into something that Zeiss can run. Let's see, another element that we've had to work on, and I'll talk about this on the next slides, is we've had to completely rewrite the expression library, and I'll explain why that is in a minute. And then also, in order to support modern industry standard models, we've been using the ADMS Verilog A model compiler, and I'll talk about that a bit more in a minute. So in terms of what PDKs we have supported or used, basically I've seen examples, and I've done this myself, of running circuits using the PDKs that are listed on the right hand side here. In general, once you get to the more modern ones, it gets harder and harder to work with it. Well, it gets a bit harder just because the commercial vendors are a lot more restrictive about who is allowed to see them. And also, if I want to collaborate with somebody outside of Sandia who's developing a circuit in a modern commercial PDK, I have to have a non-disclosure agreement, a multi-way non-disclosure agreement between them and the foundry and us. And so that's often kind of difficult to set up. In practice, it has been fairly. I've been successful in getting non-disclosure agreements set up with global foundries in the past. I have not been successful with TSMC. So that's one reason you don't see very many TSMC PDKs listed here. And that's also a reason why I'm pretty happy to see there's this move towards open sourcing PDKs, because that just makes collaboration a lot easier. So let's see, I mentioned that we had to rewrite the parser. Or not the parser, the expression library. So expression library is a chunk of the parsing that Zeiss has to do. Most PDKs have really a lot of fairly complicated expressions in them, setting up dependencies of different parameters on each other and stuff like that. And we've had an expression library in Zeiss going back to the beginning of the project, but it was poorly designed, and it had a lot of technical debt in it. And basically that technical debt came due when we started to try to run the Global Foundries 12-nanometer PDK. That particular PDK had enough expressions in it, enough parameters in it, that we were getting expression trees that were really, really big. And because of a fundamental design flaw in the old expression library, I think there was like an end to the third sort of search in it or something like that. Anyway, so there was something in it that was really, really inefficient. And so we basically had to make a change. And we'd had a lot of complaints about the old expression library. So basically we took this as an opportunity to completely rewrite it. So we did that, and that's using a modern parser generator. So we're already using a modern parser generator for the expression part of Zeiss. Just a lot of the other stuff that hasn't happened yet. But that basically enabled us. I mean, we basically went from being able to not be able to run anything with the 12-nanometer PDK from Global Foundries to being able to run it. So like the example I'm giving here is a VCO circuit. I think that was the first circuit we tried to run. And in Zeiss 7.1, using the old library, it just never got past parsing. And with Zeiss 7.2, not only does it get past parsing, it runs the whole thing in about 20 seconds. So it's a pretty big improvement. Let's see, I guess at the bottom here, I'm also talking quite a bit about, in addition to expression libraries, there's also been a lot of improvements in the parser performance. Mostly that's had to do with just making much better use of hash maps and much better use of not storing things we don't need to store. A lot of times when you're using a PDK, there's a lot of parameters that aren't actually used by the particular circuit that you're running. So we throw those away as quickly as we can. Let's see, I also mentioned model compilers. It's very important to be able to run all of the industry standard models. There's a handful of standard devices that modern PDKs tend to use, like for example, the BSM-CMG model. And the way we get that into Zeiss is using the ADMS model compiler. One thing we discovered when we started running with the BSM-CMG was that the code that we were producing for Zeiss from ADMS was extremely slow. And that was largely because the automatic differentiation library that we were using was slower than we thought. And so we completely rewrote the way that we're doing AD in the back end of ADMS, and that resulted in code that's about as fast as handwritten code. So we've had a really significant speed improvement from that. And basically that was necessary. I mean, the BSM-CMG prior to that rewrite was way too slow. I will mention that ADMS, it's been around for a long time and we were happy to use it. But I think we're getting to a point where I think we want to try to use something else. And so we're sort of taking two approaches here. One is that there's a new open source model compiler called OpenVAF. And so we're looking at that. But we're also internally developing our own model compiler. So at some point that'll become available, and that hopefully will work a little better. the main problem that we have with ADMS is that it doesn't support everything in the Verilog standard, and it's fairly hard to hack on it to add features to it. So that's another activity. Oh, I wanted to make a few notes about model compatibility and this only affects the old PDKs. In order to be in this business at all, you really have to support all the industry standard models. And, there's been a lot of work under the Compact Model Coalition to push standardization. But for a lot of the older models, some of which I think perhaps predate the CMC effort, the standards are less clear. So some recent examples for us is, we had the SPICE3 diode in Zeiss, but most simulators actually have added stuff to the SPICE3 diode, like sidewall capacitance models and stuff like that. So we had to add those. Another example would be the Berkeley BSIM3. The SPICE3 code that came from Berkeley is not quite the same as what's in most simulators. For example, there's some geometrical parameters, so we had to add those. So on and so forth. So those sorts of things come up, and that can be a bit of a headache to deal with, but we've worked on it. Let's see. So as far as making Zeiss compatible with PDKs, an awful lot of our focus has just been on, in addition to the parsing issues, have been on adding features. This is there's a very long list of things that we've added recently, and there's a lot of stuff that's in progress as well. And in the interest of time, I think I'll move on to the next slide here. So I mentioned the XDM model, which we use for translating other simulators' syntaxes to Zeiss. So at this point, it's able to translate PSpice, HSpice, and Spectre to Zeiss. I'd say Spectre is the least mature of those, in part because that's the farthest away from what our native language looks like. And also it's the least mature because we worked on it last. But one nice thing about doing this effort is that we've managed to develop grammars for all three of these languages. And so I'm hoping to recycle those grammars when we refactor our own parser. And so our own parser, as I showed this slide before, it has a lexicon parsing phase, and there's kind of a parallel phase in between, at least on the second pass. Essentially, we're just planning to rewrite to replace the sections that have to do with lexicon parsing with something that's much more modern. And we're still discussing exactly which parser generator to use. I used Flex and Bison when I rewrote the expression library. The people developing XDM have used Goose Spirit, so those are probably the two leading candidates for that. But either way, language grammars are usually specified in a fairly common format, so we should be able to use either of those, I think. Another thing we're planning to do as part of this is to create an abstract data model, which sort of sits, after the parsing is done. And that abstract data model will allow us to basically store the state of the problem in a binary format. And so that should enable much faster simulations. If you don't need to reparse the netlist, then that should enable much faster simulations. The abstract data model is also part of our plans for making Zeiss a bit more dynamic, so it's easier to dynamically change things in the circuit. So let's see. I think. Oh, this is just one example showing that Zeiss gets the same answer as a commercial tool this is on a SAR ADC circuit using GlobalFoundries 12 nanometer. We have a lot of other examples like this, but basically we've managed to make that work. Our hope is to get this to work without having to do any file translation at all. Right now, it still requires some file translation. And yeah, I think that's about all I have to say about this. I could talk more about the AI stuff if anyone's interested. I have a slide or two at the end here, but I don't know how much time we have. So I'm happy to take questions.
Thank you very much for presenting status of Zeiss development and handling all these commercial libraries. Can you have a look at chat? There are already a couple of questions to you, starting with Geoffrey asking very first one.
Yeah, let's see if I can find the chat. Here we go. I found the chat. Okay, let me see.
I asked if you looked at LLVM.
Oh, okay. Yeah. So let's see, I think Jeffrey's question there is first about the load balance. So, so Jeffrey says, is it good to load balance by expense of the device evaluation, or better to run all the diodes in one thread, MOSFETs in another? So I guess one thing I'll mention is we're doing message passing, so we're not technically doing threading. But as far as the load balance goes, I mean, we've kind of experimented with a lot of things. I mean, for at least for our message passing structure, we've generally found that it's better to, if you're looking at a very heterogeneous circuit, like what you might see with a post layout circuit, where you have, you know, a large number of MOSFETs and then also a large number of parasitics. Well, the parasitics are a lot cheaper than the MOSFETs, and so we've seen benefit by load balancing by expense. If the circuit's rather homogeneous, then it can be fine to group them by type, as long as they're, you know, relatively similar expense. I mean, I'm guessing from a threading point of view, I mean, a lot of times you know, you're looping over device types within your load phase of the simulator, and so I could imagine it would be easier to set up threading if you did it by type, but that's not the way that we did that in Zeiss. Let's see, Kevin asked about LLVM. I am somewhat familiar with LLVM. I haven't looked so much at the parser, but I actually, when I was developing the expression library, I looked at having it generate LLVM code to evaluate it. That was mostly as a test. That's not part of what it's about.
Yeah, I kind of looked at it
It's in
as
the public version of Zeiss.
they have a debugger. You know, there's
Yeah.
a debugger, and you know, my view with a lot of this stuff is you want to start with the debugger and not worry about the optimization.
Yeah, well, that makes a lot of sense. I mean, I guess part of it is that, you know, I mean, one big fear I have is that we'll replace the parser before it's fully baked, and then we'll wind up with something way slower.
Well,
So,
yeah, I think one of the things is Zeiss is I find it's a very large, massive code, and you kind of sort of want to break it up into something more modular and more plug-in like.
yeah, no, that's a fair comment.
You know, so something like HSpice and Spectre translation is, you know, if that's a plugin which is kind of separate, which people can hack at themselves, then, you know, that becomes a community thing you don't have to worry about.
Yeah, that's a good point. I mean, we definitely should make Zeiss more modular than it is. That's a fair criticism. So, yeah, let's see. So Mohammed's question: are you planning to integrate the translator in Zeiss? Yeah, I mean, hopefully my talk answered that question. We're planning to, well, we're basically planning to recycle the grammars that we developed for the translator, and then use those grammars with to set up a modern lexer and parser directly inside of Zeiss. So hopefully a year from now or something like that, it won't be necessary to run the translator. Zeiss will just run. Let's see, comment about TSMC. Yes, that's my experience as well. Experience open source Skywater. So I've been interacting with the Skywater community a fair amount through their Slack channel and so on. So most of the people in so I guess, first of all, the version of Skywater that I have used was, I think, the one Tim Edwards converted to run in GSpice. And in GSpice is not 100% the same as Zeiss, but it's closer than what I've experienced with a lot of other PDKs. It also has the advantage of being a relatively old PDK, so it's not using quite as many exotic expressions and complicated expression trees. So the people who have run Skywater have, to the extent that they've needed to translate files, they've done that themselves. And I think Matthew Guthaus from UC Santa Cruz posted a recipe for doing that on GitHub somewhere. A lot of the steps in that recipe aren't necessary anymore. I use that as feedback to improve Zeiss's compatibility. So I think it's fairly close. And so I think we can't quite run it natively, but it's very, very close. The biggest thing that was holding it back a little while ago was support for sub-circuit multipliers, and we implemented those last year. So anyway, there are people that are running Skywater PDK, and the translation is not too bad. Mohammed is mentioning he has issues with binning, so I'd be happy to chat with you about that. Sorry, the binning isn't working quite Or is, or actually, is the binning a problem on Skywater's side or is it on Zeiss's side? I guess I'm curious. Let's see. OpenVIF, yeah. Very curious to hear more about that. Let's see, Jeffrey mentions that, oh, it had to install some things as root, and that's not possible. Okay, that's worth looking into. Sorry about that. Let's see, I don't know if anyone's, so I'm wondering if, so there's a new way of installing Zeiss using SPAC, which is a package manager. I'm wondering if that allows you to do that without the root. But anyway, let's see. So benchmarks, I mean, we've done a fair amount of, we do a fair amount of performance testing on Zeiss. My experience in general is that we're not as fast as HSpice. HSpice is blazing fast. Although one thing I've observed with HSpice is I think sometimes they're blazing fast because they've taken some shortcuts. My experience compared to Spectre is that we're pretty close. And I think, well, hopefully nobody from Cadence or Synopsys is going to yell at me about this, but my experience with Spectre is it tends to be a bit more accurate than HSpice. Let's see here. So Tim has a question. Is the Ivor log co-simulation considered a valid way to do? So, and that's sort of, so let's see. So we've developed a mixed signal interface for Zeiss. I kept wanting to say mixed mode. We've developed a mixed signal interface for Zeiss, and it's been called from a variety of digital tools. You can call it from Verilog, but it doesn't. But we've also had people call it from like PyHDL and stuff like that. As far as the Y digital components goes, I mean, those were mostly developed to mimic the equivalent components that were in PSpice a long time ago, and they've never worked super well. And we should probably revisit improving those. Let's see, question from Kevin. Can you tune the parallels into the matrix hardware? Yes, there's a fair amount of tuning that if we're running truly in parallel, where we're doing a true sort of, especially when we're doing both the device and matrix part of the problem in parallel, there's quite a bit of tuning one can do. I will mention that we mostly haven't ported Zeiss to GPUs. That style of parallelism hasn't worked that well. Or I should say it hasn't worked enough better than the original parallelism that we did so far. Although one exception is actually the ML-based models that I mentioned earlier. If you're running a Python model that's invoking PyTorch or something like that, that obviously will invoke a GPU if it's available. So hopefully I'm making sense. I feel like I'm getting less coherent as I talk. So I guess maybe I had too much coffee.
It's quite early morning in New Mexico, so maybe one more cup. Yes, I think we have to kind of speed up the 3 more presentation. Otherwise, we will go beyond the allocated time. We will have Mehdi talking about his experience using open source EDA tools for free PDK of Skywater. Then we have Matthias Bucher. He will give an update on AKV and its implementation into open source tools. And the very last talk today will be by Tim talking about his work on Skywater library compatibility with Spice. And you, Eric, you address a couple of points, so there will be a continuation of this discussion. Before I will give the floor to Mehdi, Rob, can you assign Matthias Bucher as panelist? He will talk after Mehdi about AKV model.
Yes, let me look at doing that.
Okay, great. More. So I would like to thank you, Eric, for your Zeiss introduction, discussing all the details, in particular compatibility with commercial libraries. If you don't mind sharing your slides, I will upload this on MOS-AK
Sure.
website afterwards. And,
yeah, I was just going to address, Marcus had one question about AI and Verilog A, and I'll just say that we have actually done that. We've implemented AI-based models in Verilog, so that is a thing that you can do. So, anyway,
yeah,
sorry to interrupt.
Marcus and his team, they are doing great work developing open source Verilog compilers. So all are looking for this alternative to ADMS. And now we have Mehdi. He will talk about his experience introducing open source tools for design using Skywater free PDK. All
right, thanks, Vladek. So I tried to tweak a little bit my slides to match what we're discussing here. The idea behind the workshop was initially to talk about how we can improve the technology design loop here that we discussed with Rob as part of the CHIPS Alliance activities. And but I'll go through a little bit of the work I've been doing and how I encountered the open source tools and how we're trying to improve them as we go. So the talk is lowering barriers to chip design using OpenFA-SOC. OpenFA-SOC is a framework that started, or it's a corollary of FA-SOC, which is a DARPA program. So let me just move to the next slide. So FA-SOC started with the OpenRoad and other tools as part of the IDEA program. I think ZEISS is part of it as well. It's a multi-university and industry effort. We are part of CHIPS Alliance, and we teamed up with ARM and Virginia and Professor Wenzlaff was the lead of this project here. We have a couple of talks in CHIPS Alliance, so you can go and take a look at them. And I listed a couple of papers we had. Throughout the program, over the course of the program, we have successfully taped out a good number of SoCs from GF12 to TSMC65. We demonstrated some of them at the URI Summit, and that was successful. And as we, as the open source PDK was released, we started taping out more chips in Skywater and experimenting more stuff. So I'll go through that later in this presentation. But before now, we are labeling ourselves as OpenFA-SOC, which is open source fully autonomous SoC synthesis tool. We are part of CHIPS Alliance. I'm chairing the analog working group with Rob, and we're discussing a lot about how to make analog generation and custom circuit generation more automated using open source tools. Now we are funded by Google, NIST, and a couple other people. And in our framework, we are not only using a cell-based approach, but we're using tools like GDS Factory, and sometimes we call Align. So it's been a really great, evolution of our framework. So how does it work? I think it's important to explain our framework here. I made a small workflow diagram on the left of what would be a traditional analog layout flow today. As you all know, most of it is custom and require multiple iterations from schematic entry to layout, then simulation, and so forth. The digital flow, however, is fully automated, right? And we can call it a grid-based flow. So the idea here is to basically take what would otherwise be a full custom analog layout and shoehorn it into the cell-based digital automated design flow methodology, which is very amenable to the available logic synthesis and place and route tools, be it proprietary or open source. So you've heard that a few times now. We use a cell-based approach, and the idea is basically to divide and conquer. The experience we had with fully automated or custom-based analog generators is that it's very hard to bring them up, and it's PDK dependent, so it's really hard to come up with a test case and port it to a new technology. So a really simple way to understand this is, or what we are doing is that we try to describe analog blocks in Verilog, and that can be either be a structural Verilog, behavioral, or combination of both. With the structure of Verilog, we plug in specific cells that are identified as critical analog functions to your generators. This could be either from a traditional standard cell library or a library that has been augmented with a couple of cells, and we call these cells as auxiliary cells or aux cells. So to demonstrate our framework, we identified a couple circuit diagrams or analog blocks that we have published in ISSCC, VLSI, basically flagship conference circuit conferences. All these structures have been taped out before and published. These are legacy designs that have proven their results on other nodes. And I highlighted in blue the example of auxiliary cells. So for designs like SAR, ADCs, DLDO, stamp sensors, PLL, and switch cap DC-DC converters. So each time the analog functions is either an auxiliary, an header cell, power switch, a fly-in cap, a comparator, and so it's usually a 12 below transistor block, and that is easier to tackle, especially if it defines the analog functions of your design. So then, after creating a template of those analog structures, we use different automated ways of modeling the circuit so that we can cover a design generation for a wide range of user input specs. So this diagram here on the left basically summarizes this. Yeah, I think these are the auxiliary cells. They usually take a day or two to make based on the innovation you want to make, or let's say you're porting from SkyWater 130 to Intel 16. You don't have any native transistor, for example, or any other exotic devices. So and that requires you to rethink a little bit your sensor or any other block. So in that case, what we do is we try to accommodate the auxiliary cells in a way we can port the design from a SkyWater 130 technology, which is a much older technology, to a FinFET technology, and that has been working fine. We just recently taped out an Intel 16 chip that is showing really good PEX results. But in general, these are the auxiliary cells. They look like standard cells. They are 12 transistors below. We try to use different frameworks, for example, Align from Minnesota and Intel, to basically automate this last piece of OpenFA SOC. It has been a little bit challenging sometimes, especially when we go on advanced nodes, but it's still working for some of our auxiliary cells. So it's I think it's it's a trade-off on how much you want automation versus custom design. But the idea here is basically, if you are able to define different auxiliary cells, you are going to be able to generate thousands of designs, and that's actually very interesting, especially in the open source tools where you don't have any license or requirement, or you don't pay for your license. So you can generate thousands of hundred thousands of designs and basically come up with an algorithm to decide which design is best. So I think this is very, very promising, and we'll see much more of it. I'm kind of excited to try XICE, which has a lot of parallelism and multi-threading, so we can run a lot of simulation and verify that our idea is working here. But data-driven optimizations make a lot of sense here for analog design. So FSOC relies on a set of proprietary tools and wrapped inside the cadre flow developed by Professor Ron Dresdinsky from Michigan, and it is an abstracted layer over the closed tools. But now, using open source tools, we are heavily relying on OpenRoad among other tools. Also GDS Factory. I'll try to discuss that later in this presentation. But there's a couple other tools like UOSys ABC for logic synthesis, Sherlog UHDM plugins integrated by Antmicro and Google for system Verilog support, Magic, NetGen, and KLayout, thanks to Tim Edwards, who's here, and also ngSpice and XICE. So we don't really have a full support of XICE yet, but I think that's one of the action items we have for the next months. What are the trade-offs? So, okay, this diagram here is trying basically to explain why we tried the cell-based, why we use the cell-based approach. And the reason is, if you spend some time porting a design to a new technology, it requires, or basically doing a full custom design, which is all the way to the left here. You require 100% complexity. And compared to the initial version we had, which is FSOC 1.0, which is standard cell only based, we had minimum constraint and digital compensation. So that was 4 years ago. And what we tried to do is basically include some partial constraints of the digital flow, like fencing, non-default rules, voltage domains, to basically accommodate some of the needs for analog design. And when we do that, we swing back into the middle, where we can see that we can get the best of both worlds. So in fact, in using our cell-based digital approach, we are in reality avoiding the extreme complexity of trying to take in all the PDK DRC rules that comes in with full custom automated layout, like routing and active layer drawing. Also, with the rule of diminishing returns, the time required porting to a new PDK or even a new design topology would essentially make an automated flow or full custom analog generator too costly to make across PDKs and test cases. And we have seen precedents in that. So I think we have here a sweet point, which I fundamentally believe we could push more to the left using open source tooling and automation. And I'll discuss that later in this presentation. Here's a few examples of what constraints would look like for a PLL, where we gave extra attention to the DCO block. We are using Python scripts to structure the placement of fine and coarse cells, where all the cells are sitting tightly on fairly wide stages. The DCO sits then right into the middle of the rest of the PLL, which is all placed and routed and surrounded with end caps and D caps. The block has been taped out in GF12. And I think it has been published recently in RFIC. Another example is for power regulation, a digital LDO which taped out in different technologies, including Skyward 130, GF12, and TSMC65. You can see the pre-pack simulation of the max load current versus the array size of the PMOS switches, where everything looks fine and smooth, but then after running the design to APR with minimal constraints and random placement, we see after post-spec simulation that the max load current takes a toll and goes way down. So, and as we increase the array size, we can clearly see that the variations and resistive effects due to narrow routing or minimal via cuts. So to address that, we came up with a more structured placement of the switch array, as well as fencing some of the cells. We also did automatic PDK parsing of its metal stack info to calculate resistivity over the power stripes mesh. We can see that the performance is considerably improved with the smooth curve we see in the pre-packs. And we get back the max load current, as you can see on the top right plot. So these are examples. There's many of them, and it depends on the technology. These are very low-hanging fruits, so I can go on for a couple slides, but I'll stop here. So a couple other things I want to discuss here is the open source tapeouts or fully open source tapeouts we did. One of them that we published recently in solid state circuit letters is this array of sensors. This was done in the first shuttle, and it took about a month or a little more than a month. And we included, we basically plugged in this framework to the open source tools and tried all the flavors blindly, basically, or almost blindly, to see if our sensor is going to work, because we didn't have much time and there was so many issues in the first shuttle. We also came up with, since we were we were design advisors of OpenRoad, we kind of driven a little bit the features included in the router and placement. So here you can see that we added a non-default routing, which was used basically as a special routing for the power domains. And we also included the power domain here, as you can see, but it's kind of rudimentary, but it works for our needs here for analog design. These are the measurement results. I'll just go later a higher level. I don't want to bore you with the details, but basically, if you make 64 sensors, you can map out what is possible in this technology with different features like high density sensors. You can squeeze the size, or high speed, where you can have a better inaccuracy or a time conversion. So this is really good for foundries to experiment in their designs or their capabilities and sell their technology. But basically, we got really state-of-the-art results, even if we designed semi-blindly our temp sensor. This is in inaccuracy. This is below 1 degree C inaccuracy, which is state-of-the-art. This is a table of, or summary comparison table of how we compare to other published paper in ISSCC or CICC or JSSCC. I'll share these slides. You guys can go through this table if you need. But one thing I want to bring up here is something we discussed with Rob, which is the technology and design feedback loop, and how we can take the chance of having this open source initiative or movement happening, and we can improve this whole loop and make it, available to everyone. I think there's a real issue between tools compatibility. The models doesn't run if you run the closed tools. That was my experience. I don't know what others had, but I'm not able to run simulation using closed tools to do comparison. So I had to use the proprietary PDK to do my analysis here. This was done 2 years ago, so maybe things changed. I don't think so, especially on the model side. So we're working on that. There's a real issue with the quality of the model, so we're working with a couple other people. I think CoolCAD, Akin from CoolCAD is doing a great job there, especially at cryo temperatures, but also Christian Enz from EPFL we are working with to measure the chips we made, or also the proprietary tile from Skywater. But here, one thing I want to note here is that even if you designed blindly, it wasn't, it was for a reason, because this is what NGSpice is giving me in terms of inaccuracy, and we're getting up to 3 degrees C. When I use the proprietary PDK or closed tools, I'm getting something closer to what I'm getting on silicon, and it's still not great. This is just the closest I got. So in terms of power, especially at -40, 125, we are basically, out of the window of the models, right? So I think this is a real issue that we have to resolve, and I'm hoping here we can discuss it with the right people, and also through the Analog Working Group in Chips Alliance. Yep. So yeah, this is the second shuttle. We didn't stop there. I mean, the model issue didn't stop us. OpenFA-SOC is good to generate a wide range of designs, as I said. So we can actually design later semi-blindly, but we can, based on our experience and previous nodes, we kind of know exactly where to target our designs. So in the second shuttle here, we taped out an array of digital LDOs with voltage reference and analog buffers. Also included a root of trust called OpenTitan. We included the temp sensors second version, we included a couple other things in terms of flow to be able to do this work here, especially on open road. But basically, we included the voltage reference, highly tunable voltage reference, to account for the bad models and variations. We added DCAP, VF, and DCAP cell generator, and we made a couple different switches using different structures or flavors, like native NMOSs or PMOSs. This is a simple LDO, but it's kind of enabling people, they can reuse this and show the capabilities of using a cell-based approach. This is MPW2, so we co-integrated the LDOs with the root of trust, and we hopefully going to get the chips back soon. So that's going to be great to see if this is working. We also developed an ECO flow to fix the hold violations that we kind of encountered and we were aware of a while back. And that's about the tape out for MPW2. The other thing that I want to mention in this presentation is test structures, and it joins back my discussion here about modeling and how would the technology design feedback loop looks like in the open source realm. Basically, this started with NIST, CoolCAD, and ADSR. And this was led by Brian Hoskin from NIST, who's a physicist. But basically, we want to create models for cryogenic temperatures. I won't go into the details of the needs. Should have removed these slides, but basically, we had to make a test style that would be useful for people to make new models, measure them, and make new models. And I think that's what CoolCAD is doing right now. This work is done under the umbrella of the partnership between Google and NIST, and we taped out this chip on MPW5. But during this tape out, we started diversion a little bit from the cell-based approach. We started using tools like GDS Factory, where we started before GDS Factory, we used OpenRoad to do this ring oscillators that needs to fit to fit the 40 by 40 footprint. These are connected to the bare pads, and there's some fencing here going on with some interleave placement where we used Python to do the interleave placement and manipulation of the diff files. We taped out, this is using OpenFA-SOC, so we were able, again, to port all the standard cells to this 24 ring oscillators in total, and including the OSU standard cell libraries done by James Steins from OSU University. This is the structure we made using the GDS Factory. This is made using Python, and those are really low-hanging fruit because what you can do, what we noticed is that we can make a function to do an array placement or mesh generation. And those functions are kind of generic because you can just make it, you take in the dimensions, the pitch and layers, and we can reuse that for different blocks. So this is a memcap array. We used it for the diodes. We used it for flying caps for PMU. So I think this approach is great, especially if you need fully custom layout generation in an automated manner. So these functions were reused. So we generated this array, but we also generate this other array here. And we kind of called the same or some of the same functions, Python functions to do that. And GDS Factory was really great because we could, the framework there is very hierarchical. It's meant for photonics. So we kind of tweaked it a little bit to do what we needed, but I think there's a lot of work done by Joachim to adjust for the ASIC design. So at the end of the day, we had 1,400 pads, a lot of transistors, and this is the resultant die. These are our partners from NIST, ADSR, and CoolCAD. We had a lot of other people join in later on from GWU, Brown, and CMU, who helped us through this tape outs. But one thing I want to note here from this these shuttles here, or these test harnesses, is that as we went from MPW5 to MPW6 and 7, this is 3 months time frame. This is a very high pace of taping out, but we still could manage it while using OpenFA-SOC. And you can see that the complexity is getting a lot more, a lot higher as we go through the shuttles. And I'm sure in MPW8, we're going to tape out some quantum current standard structures that will look a lot more complex than this. So this is great to see, and hopefully we can have more adoption and interest from the community. So this is what OpenFA-SOC looks like today. This is, just this is not an up-to-date diagram, but it just basically shows you that we're calling new tools like GDS Factory, and we call in Python APIs to manipulate def, but also to do manipulations in GDS Factory as well, or massage the layout to get a better performance as we go. So this is the end of my talk. Hopefully was interesting, and please let me know if you have any questions.
Yes, indeed. A great presentation, huge collaborative effort, and all what you presented was done using open source tools. This is something unique, and I hope all will appreciate your work, and there will be even more followers exploring the same path. If you can look at the chat window, there are some questions. We have still time for
Sure.
2-3 more questions.
Yep, I see the comments from Mehmet. Yep, I agree with that. Open source tools are auditable, so you can check the source code and see if there's any, modification. How do the MOS sizing problem was to get access? You mean the binning problem in Skywater 130? Is that the question?
Or maybe it's about analog design and sizing transistors for matching.
Well, I mean, we do a lot of when building up the generator from ground up, we run different configuration, or basically just porting it, right? So we run different sizings. Usually we start with minimum sizing, and we just go as we we increase the size with small steps, and then we can get a sense of the direction. But the whole modeling part is kind of automated. So when we have to do it from Skywater 130 to Intel 16, we actually just run the same framework, but only by modifying some of the tools that are called, or test benches, and simulation time.
All right, and you are using a layout tool for layout optimization. So it's yet another open source tool to improve the layout of analog circuit or subcircuit.
Yeah, well, usually since this is a cell-based approach, the auxiliary cells are the only cell that we require to, that takes a lot of time, or a bit of time to design. So basically we spend a lot of time, we consider a lot of sizings, and we run the whole generators since like 2GDS and PEX, and we can get an idea of what the performance is going to be. And I think that since that loop is automated, you can do much more as you go from a technology to another, or from a test case to another. Like think about changing a fly-in cap or a switch for a PMU. Then you can try different switch structures for a SAR, recursive SAR, DC-DC converter, and you can get different efficiencies and results as we go, or drop. Hope that answers the question.
Okay, so there is a appreciation of your talk in the chat window. I think we are ready to move to next presentation. Again, thank you very much, Mehdi, for your talk. I'm sure all would be willing to follow your path, and we can draw more attention to open source tools and design automatization.
Definitely. Thanks.
I think it's a little bit question on other topic about parameter extraction, but maybe this question by Sadayuki we can address offline. We do not have any presentation on parameter extraction at the moment, but maybe following talk on AKV indirectly will also address parameter extraction. So I would like to invite Nick Macris. He will be talking about AKV free development, and it plans to release the model as open source code.
Hello, let me share my screen. Just a minute. Okay.
Yes, we can see full title page. So,
okay.
The floor is yours.
Thank you. Hello, my name is Nikos Makris. I am a PhD candidate in Technical University of Crete, and I am working with ISL 4th in GaN HEMT and silicon carbide JFET development and modeling. I will present you today our work from Technical University of Crete regarding AKV3, and I will present you some introductory work having to do with AKV3 and then GSpice integration using ADMS XML. The outline of this work is the following. Firstly, we will discuss, I will present you a bit some things about AKV3, what the contributors, some version history, and any new developments in the model. Then I will present you the Verilogate structure of the model. After that, I will present you the phenomena covered by AKV3, what is going on about the integration of AKV3 and the usage of AKV3 in different simulators. Then I will discuss AKV3 in GSpice. We have done some simulations, and we integrated the simulation part with the visualization part in JupyterLab, a tool that I do prefer using it for this sort of work. And finally, I will present you our conclusions. AKV3 is a compact MOS transistor model. It is used in analog RF IC design. Special care is given in RF and noise performance and modeling, and the development and maintenance of AKV3 the development and maintenance are from Technical University of Crete. The charge-based approach actually it provides us a smooth transition between the different operation, different inversion regions between weak, moderate, and strong. The charge-based expressions help us to write the equations that finally we will avoid convergence problems. AKV3 is the successor of AKV 2.6. Utilized in it has been used in various CMOS technologies and commercial PDKs. Several model variations. We have made several model variations in order to cover different R&D needs, and it has been distributed to Keysight, Cadence, Synopsys, Zeiss, and other vendors. So This is a list of contributors of EQV3. First of all is Professor Matthias Bucher. Antonius Bazigos was with Professor Matthias Bucher, were first to edit the model, the first version of the model. After that, Maria Halkiadaki, me, and Nikolaos Mavridakis have contributed and in testing implementations and debugging. Furthermore, other contributors are François Courbenacher, Michel Saleze, Christian Etz, Eric Pitos, Ananda Roy, and Dr. Grabinski in code standardization. So EQV3 model started as a model on March 23, 2005. Up to this point, we are in version 3.2, which is the currently distributed in most of the tools that are in the most commercial tools. Okay, the EQV3 as a model, the very good as a structure. First of all, we have we are using different instances of the model like DCS, DC, in order to simulate DC and analog operation. RFS and RF provide, as you can see in the graph, provide additional nodes and resistivities, and in order to incorporate phenomena, RF phenomena that we want to simulate. And an NQS instance is also available, which actually where actually we have segmented the FET channel, the MOSFET channel, in order to cover the non-quasi-static phenomena. In version 3.2, we have imported operating point information, charges, normalized charges, current voltage nodes, etc. We have incorporated an enhanced flicker noise model, and several bug fixes have took places. Now, regarding the EQV, the file hierarchy, we have the EQV3.va core model, which has the main functionalities of the model. Externally included files of other phenomena like noise, overlap capacitances, edge effect, jiggle, series resistance, hysteresis diodes, bulk current, gate current fringing, and of course some functionalities like model variables and parameters, debug information, and operating point information. The phenomena that are covered from EQV3 are basically first of all, the core model, which is the physical modeling of the charges, the bias-dependent overlap capacitance, the number of the non-quasi-static behavioral, the RF behavior, mobility, impact ionization, current, gate current, lateral field effects, velocity saturation and channel length modulation, reversal channel effect, inverse narrow width effect, dipole, source and drain charge sharing, hollow pocket implant effects, edge conduction, geometrical effects, width and scaling, noise, where we are using two models. The first model is the standard model that it was included in the previous versions, and in the newer version we're using a version of for the flicker noise, which is a McWhorter hoods and drain source axis noise models. The temperature effects are covered using various parameters. The total parameter set is actually 226. So EQV3 in simulators. In order to incorporate using we are using the EQV3 in order to use a compact model. There are actually three ways that we have used. The first one is the embedded model in the simulator, meaning that we will provide the code to Keysight, to Cadence, to Zeiss in order to incorporate it in their simulators, or we will do it by ourselves using the open source simulators like NGSpice, which actually where we provide Verilog code. The Verilog code is translated using ADMS XML and the XML files that are dedicated to the model to C++ files, and then it is compiled and we generate actually an executable. We have some externally. Second way is externally loaded Verilog code, using an include statement in the model card, which is actually compiled into a shared library during the simulation time. Again, I think using ADMS XML, like in Spectre, in HCP ESOFSIM, or in Coax, where we have used EQV3, some forms of EQV3 for educational purposes and for research purposes. The third way is the pre-compiled form of the model as an external library, which we have used in some R&D projects using the compact model interface of Spectre. The possible limitations and issues regarding the use of ADMS XML is that sometimes not all the features are supported, like in NGSpice, that where we cannot the Verilog model. The process of the translation does not produce any noise files, and when you are using different simulators, you use different XML files which are dedicated for this the type of the data structure that the simulator has, and then meaning that we have a different code interpretation, and then we have seen some different problems while the process. The EQV3 in NGSpice, the first time that we used EQV3, it was in 2014. And we published a paper with that. We used it in order to incorporate EQV3 in NGSpice, and then do some simulations in order to model RF measurements, and in order to qualify and see if there are any differences with Spectre. The usage of that version was actually almost dedicated for experimental and teaching. It was oriented for experimental teaching. Now, in order to use the new version of the AKV3, we try to incorporate it in NGSpice version 3.8. Over here we have some details about the process. We have to create some folder which is dedicated for AKV3, configure the configure.ac file in order to provide the to generate the configuration files that are needed in order to compile to extract the C code and be compiled during the process. The XML files, editing XML files in order to recognize the DNS XML that there is a file over there, that there is a model that it is called AKV3, and in order to extract the code, AKV3 noise.c is generated in order to compile in order to include into the compilation the AKV3 noise.c file. We need to further edit NGSpice makefile and module init.c XML files. And lastly, we edited dev.c in order to the simulator to get the model information, the inp do mp&d.c, which is the file where you say which level you will which level number you will use for this model, and the inp2m.c file, which is actually the parsing, the parser that recognizes that when in the line, when the line starts with an M, means that it is a MOSFET and that the AKV3 is a type M device. For experimentational purposes, we have integrated, we have done some work, and we will continue this work in order to fully implement the noise model in the NGSpice. As the first step, we have started using the BESIM1 C++ code of noise, and we have altered it in order to provide some results. After the alteration, the update of the code, we do a recompilation in order to have and the build in order to have a new version of the executable and use it. So the whole process was done in Linux Mint. We have generated Linux standalone executables and Windows executables without GUI, and I will explain why using a cross compilation. The idea was that it would be nice to have a more interactive way to simulate to make simulations with AKV3. So we used the Jupyter Lab, which provides a quick and easy visualization of the simulation results, and we are easily it is easy for us to manipulate the data that are the simulated data. So we used Jupyter Lab, but in order to run NGSpice in Jupyter Lab, it has to be in batch mode. So if you are running in batch mode, the executable, you have to exclude the GUI from the compilation. The libraries that we used for the results that I will show you in the next slides are matplotlib for plotting, pandas for dataset manipulation, OS for instance spice execution, spice for raw data input. So this is a sample from the deck of the Jupyter Lab. As you can see over here, we make a list of the measured data. The data are from a MOSFET with width 3 microns, I think, and length 100 nanometers. So we have the list of the data over here. Then we have a function which actually makes the simulation, which actually modifies the simulation file every time for, let's say, V-drain or for the bulk potential. Then it is written in the disk. Then it is executed using a DNG spice. The data are retrieved by using the SpiceI library, and then using the data frame, we can take the simulated data. And this routine, actually, what it does is the plotting. It is plotting the measured, which are the symbols, versus the simulated, which are the blue line. And these are the results of the simulation. As you can see, the model card that we have used has a very good fit in the IV. A second simulation was a simulation of AWG versus V-gate for different bulk values. And as you can see, the routine is very easily modified, and the code can be easily modified and reproduce the simulation results and produce the simulation results. Over here, we see the same graph, but in logarithmic scale, and we see something that it is that AKV3 has in for a very long time, which is the edge conduction, which can be seen over here. This hump is due to the fact that we have actually two devices conducting in parallel, and which is which is a phenomena that needs, which is due to the STI. Now let's go to the next one. The next one, the code over here generates the GM over ID, and you can see the edge effect is more pronounced in this graph. The fit is good. Then we go to the execution of the output code. The logic is the same, using the same using a similar routine, and this is the results that we take. So unfortunately for the noise, we need to do some more extensive work in order to provide to see if the results are the results that we should take. So that's why I haven't included in the presentation. So for as a conclusion, EQV3 is a robust chart-based compact model which is used for many years in commercial PDKs, covering a large number of phenomena. EQV3 has been embedded and used in commercial and open source simulators for many years, and we hope for many years from now. EQV3 can be embedded in the latest ngSpice 3.8 using ADMS XML. We will do the special effort in order to make the noise model integration. The combination of ngSpice and Python and Jupyter Lab reveals an easy way to visualize and manipulate simulations using open source and free, actually, tools, which is quite good for teaching purposes, but and for research. We would like to go to an open source version of AKB3 in a few years. We will not stop in developing the model, and we have a lot of ideas and new things to import to AKB3, like new statistical behaviorals of noise and edge compaction, and so on. Thank you very much for your attention.
Thank you very much, Nick, for your presentation, introducing or reintroducing AKB3 model, showing its implementation procedure and analyzing its performance. I'm also happy to see my name in your presentation for my tiny contribution to standardization efforts. If we have some questions from the audience, we can briefly review presentation now. I guess the main question will be about timeline for you to release AKV as open source. What your estimates, how you see development and eventual ability of AKV model as open source?
Okay, I think that we cannot say right now about the timeline due to the fact that we have to do some internal talk in order to see what is the best way to open the code, and which will be the best way in order to be and bug free. Let's say in order to have we will need some time in order to continue our debugging and result to a version that will be even more stable than the one that we have right now. So this is something that Professor Bucher could answer. Maybe it's not my position to say right now.
But on special request, one can have model AKV3 model implemented in ngSpice, Zeiss, or Quarks for simulation and further model evaluations. I guess as binary code is already available in open source tools.
Mm-hmm. Yes, it could be actually. I think that this would be a good way to start, and we are going to do it, but it's not right now the time to do it. We are in the middle of the process right now. We are trying to find time and make it as good as the code, and finalize the code in order to be able to say that we will open source it. In other words, maybe let's say that it could be a version like the code will be ready. Let's say that for ngSpice, maybe we could provide the code for the model, and not the Verilog, the Verilog, and be like Besim 4 or Besim 3, which are incorporated in the ngSpice. But we will be there I think that we will be there in a while.
Okay, very well. So we will be waiting for, yes, there is a question in chat from Sadayuki. Can you read, or shall I read this for you? Or?
Can you read it? Who is? Sorry.
So the main question is, what is the technical difficulty to implement the noise model code to in AKV, and what is the main issue or bottleneck?
The noise model is there. The AKV3, the Verilog A code has already incorporated it has the noise model. The difficulty is not the open source as open source. The difficulty is the fact that NGSpice that we are working right now does not support the extraction of C++ of the code, which will make the simulation of the noise ready.
Can you guys hear me?
Yeah.
Maybe if I can comment, I'm working with
Yes.
Pascal on the OpenWeb compiler and the NGSpice team.
Mm-hmm.
We are right now almost finished with the OpenWeb integration. I mean, everything is working. We're working on documentation now, and we plan to throw out ADMS in one of the next releases. So I'm not sure how reasonable it is to spend lots of time debugging this ancient interface when it's gone probably beginning of next year.
Okay. Then we will use the new version.
So we would be really happy actually if maybe we can give you, I mean, it's already everything public. We can send you an email. Maybe you can try it. It's working already in the development branch.
Yes, yes, we will be happy to test it with our
And
code.
that's also the answer to Tim Edwards' question, by the way. Thank
Yeah, it's more general question about NGSpice. It does not support plugins or dynamic libraries, and it's more general. All right.
I mean, the way we do it now is completely dynamic, nothing with compilation anymore.
Yes, originally it does not support, but with your recent development, you found the solution. So I think this is really worth to explore path and do further investigation, or really using your compiler for new model
I hope that we can give a talk at one of the next MOS-AKs.
Yes, I'm looking forward. This will be of interest to all. By this, let me close Nico's presentation on AKV, and we have to quickly move to the final talk. Tim will give an update on his work on Spice or NGSpice compatibly for free Skywater libraries. This is a really important topic to discuss. I hope that also Rob can extend our meeting beyond 2 hours limit. So Tim, it's now your presentation.
Yeah, that's fine. And I will keep this short. I don't have all that much to say about it, so it's a fairly targeted presentation. It's a fairly targeted thing that I did, and I've been asked to talk about what I did for doing the model conversion to NGSpice support in the Skywater Sky 130 PDK. And I've never done a presentation for this before, so I just threw this together. And pardon me for not going full screen with this, but the last time I went full screen with something on this computer, it crashed my window manager, and I had to log out and log back in. So I don't want to do that.
It looks fine
I figured
on my side, so it's okay.
Yeah, I figure it's okay.
Yes, please.
Yeah, so the idea is that we wanted to make the Skywater PDK compatible with open source tools. And at the time that I was doing this, I did not have access to Zeiss. I wasn't that familiar with Zeiss. Zeiss was in early stages of development. So I was pretty much ignoring that, concentrating on NGSpice. And I'm very happy that we've been able to work with Eric Heider and his team and get some Zeiss compatibility going with that. But this is sort of predates all that. In fact, the first indication I had that I could potentially just simply take a Spectre model or a whole Spectre library of models, the entire PDK, and convert it into something that is NGSpice compatible came from this, from Thomas Benz at ETHC, and he has this repository on Codeberg. And he presented this at a conference back in Zurich, I think about 5 years ago or so. And it was just a surprise to me that, oh, is it that simple? This is just some Python scripts, and he did a conversion. He was doing the conversion on the fly. So I ended up not using this because I wanted to actually create a version of the PDK that was completely compatible with NGSpice. Whereas what he was doing was having some scripts that would read in the whole Spectre libraries as you did the simulation, and then convert them on the fly into something that you could plug into NGSpice. So I did it a little different way, but it was the impetus for the whole thing. So the main thing that I did was I was working with Tim Ansel on the Skywater 130 PDK. He's a FPGA guy, so he does not really know much about analog or device physics or devices or the lower level stuff in the PDK. So he threw that all on me to try to figure out how to do it. And I had been working at eFabless with other processes like XFab, for instance, and they had, I guess it was mostly HSpice models. And HSpice, as you may have figured out from some of the earlier talks, is a bit more compatible with NGSpice than Spectre is. The problem we had here was that Skywater didn't have HSpice models, or at least we didn't get any for the open PDK development. And so I was stuck with the fact that I had a PDK that was done entirely in Spectre and had to make it NGSpice compatible somehow. So I was responsible for putting together all these scripts that did the conversion from Spectre to NGSpice, and that stuff is all not available because I was working with the Spectre PDK under NDA with Skywater, and ultimately that spat out the PDK that I have listed here in the URL, which is the Skywater Open PDK. But I can show you a bit of what I did in there. That was like a sort of two-stage thing, because by the time we were hurrying to get this Open PDK out, and by the time we actually got it out, I was still thinking about how to do some of these things in the conversion. And so not all of the conversion made it into the open PDKs, and I'll show you where that split is and what I've done about it. What I've done about it mainly is to deal with, this is my repository, Open PDKs, and what it does is it takes the Open PDK that Google has created, which is not necessarily in a format that is particularly usable by tools or designed for use by multiple tools. So what Open PDKs does is it takes a bunch of known open source formats like NGSpice, Zeiss, Magic, K-Layout, whatever, and it creates all the setup files that are needed in order to make a Open PDK, such as it exists in the Google repository, able to be used with all these open source tools. In the process, it also does a few things like fix some bugs that got into the open source PDK, and in this case, finish off some work that I failed to get done in time for the creation of the repository. So here's my experience with converting Spectre format to spice format. So this is just a GUI image of Spectre on the left side, ngSpice compatible on the right side. And you probably can't see all the details of it, and it's not important to see the details of it here. I'll go through a couple of examples in a minute, but the main thing is the format is pretty close. There are definite things about Spectre format that require a lot of bookkeeping in order to translate them. But on the whole, it's more or less compatible, and that's what makes it possible to just run it through a series of Python scripts. Now, after hearing Eric Heider talk about Zeiss and XDM, my suspicion is that I could probably take something like XDM and replace this whole thing, and it would work much better and much nicer. But this is what I did at the time. Some things are very, very simple, such as Spectre has portions that are already SPICE compatible. That does not necessarily mean ngSpice compatible, but you do need to track where it says simulator lang equals Spectre and do certain conversions there, and then track when it says lang equals SPICE and do certain other conversions there. For the most part, it's possible to automatically figure out whether it's using Spectre syntax or SPICE syntax. It's not that hard to figure out. Other really simple stuff to take care of is the fact that Spectre will use C syntax like comments. Those have to be converted to SPICE comments. Comments are actually rather complicated in SPICE, since you can have comments inside parameter blocks or inside continuation lines. And so it's not necessarily as easy as it looks, but it can be done. This is getting into more complicated stuff. So Spectre has this idea of an inline subcircuit. And so while it is actually possible to convert such a thing into regular SPICE. So you find this thing inline subcircuit, it is declaring some subcircuit name, which is the equivalent of some SPICE model. The pins go in a list in parentheses, then parameters are listed in a separate line with parameters. And then it calls the device, this is the oddest thing I think about Spectre, is that instead of using the SPICE names for components, such as M for transistors, then they have names that are the subcircuit. And I think the idea here is that they can recast this if you want. In some cases, you may want this converted directly to a subcircuit, like an X for a when you're calling it in a SPICE file, or maybe M if you're doing LVS on it. That's my understanding. But it makes it difficult to parse because you never know what's going to show up on the line here. You cannot just use the SPICE level component names. Further down, they put the model in. Again, it's done without a dot card on it. And they have their own way of specifying what type of model it is, instead of looking down in the parameters and seeing, oh, it's type equals 54, whatever it is for BSIM4. They've got another name here, BSIM4, puts everything into a brace delimited block for a bin. That goes on a separate line. They have recast the usual SPICE telling whether it's an NMOS or PMOS to some different nomenclature, N or P. And all of that has to be translated out. This is just a lot of bookkeeping. Some of it's just direct translation, remove the parentheses, change parameters to dot param. Other gets a lot more complicated with the, figuring out where the model bin here on a separate line goes back into the model name as a suffix. So other complications. Here's where it gets even more complicated. They've got a subcircuit this is for the high resistance poly resistor. Again, the pins go in parentheses. You've got a parameters block. This parameter block has C comments nested in it. The plus lines, which in SPICE normally go in the first column, have been indented. Also note that some of the parameters in the parameter line are parameters of the subcircuit, and some are parameters of the model. And they have dumped them all into one place here. And then they call all these things such as R body look like normal SPICE components, except sometimes they're calling them with a model name here, res body. Sometimes they're calling in with a model name such as resistor or capacitor, which doesn't have any SPICE equivalent. Those things have to be figured out. In this case, the resistor is calling a model. Normally in SPICE, when you call a resistor with a model, you're implying a semiconductor resistor, and therefore you're using width and length instead of R for resistance. But here, they have used the model just to insert the parameters for the temperature coefficients. And so I had to sort that out. In that case, you don't really want, in regular SPICE nomenclature, you don't want a model for that resistor. You want to just pass those temperature coefficients to the resistor line when it calls the resistor. So you can tell by now my parsing functions are probably getting to be several thousand lines long, but still doable. So that was that by that time. This is about how much I got done when we did the open source PDK. After that, I got to the point of the PDK was done. I was having a hard time getting Google to take pull requests on it. And so I started putting all the stuff that I had not gotten around to into open PDKs, and it just patches these files as it creates our version of the open source PDK. One of those is handling the Monte Carlo. So again, you can see at this stage, I have the open source PDK as the Google repository on the left, are one that I'm doing with open PDKs on the right, and they are almost one for one. So it's a much simpler patch job here. Where in Spectre, you get these statistics blocks. You got statistics blocks with mismatch for mismatch simulation, or process for Monte Carlo process variation. And they tell you what parameters to vary by this vary statement. This is a lot of complicated bookkeeping because the statistics block may be in a separate file from the model that's actually using the parameter that's being varied. So you have to not only do bookkeeping, but you have to do bookkeeping across the entire file system. But ultimately what happens is that somewhere in a model, you'll have an expression. The expression will use this thing that Spectre is saying needs to be varied, and that gets replaced with, first off, a Gaussian function that is recognized either by, that's an HSPICE thing and a NGSPICE thing. And then to say I'm going to use that or not use it, I precede that by multiplying by a parameter, which is either 0 or 1, which is in this case MC/MM switch. It says if it's 1, I'm going to apply the Gaussian. If it's not, I won't. Fairly simple way to control whether you're using the Monte Carlo or not. The main thing to do is, since this is a parameter and could potentially be any number whatsoever, take that out of the hands of the users, put it elsewhere. I'll get to that in 2 slides. So the other one was for the process statistics for Monte Carlo. Again, same thing, same concept. Spectre will say, here's the parameter, here's how it's varying, and you just need to go through the entire file system, find out where are those parameters being declared, and replace them with the whole expression with the Gaussian. And that takes care of the Monte Carlo simulation. Then finally, for that switch, that MC-PR switch, or the MC-MM for mismatch switch, I create a custom .lib file. And then in that, I will create corner names, such as, obviously you have your regular corners like TT, SS, FF, but I'm also creating corner names like TT_MM, which is your typical plus mismatch. And then that, inside that, I'm setting the switch saying, okay, for the TTMM .lib, if you call that, then it's going to set the MM switch to 1, it'll set the PR switch to 0, and you'll get a mismatch simulation. And that's pretty much all, quote, all I did. As I said, it's like Python of several thousand lines of Python code. But that's more or less what it took to get the open PDKs working. So I'll be happy to take any questions about that.
Great, thank you very much for your review of translating commercial library to ngSpice. In the chat window, we have some comments from, and the very first was from Dan. He was giving a pointer to his netlist, netlisting tool. Did you look at this? Do you know the recent work?
Sorry, I'm just getting around to looking at the chat window. Oh, you're referring to Dan Fritschman?
Right.
I have not looked at that. Would be happy to.
And more kind of general question, it's shall we keep all this work developing, building new translators, or maybe shift this work into simulator development? So it's like ngSpice or Zeiss, and they eventually could add this support of commercial library syntax to their tools.
Well, clearly the way that Zeiss is doing it with the XDM interface is a very good model. It's very nice to be able to say, oh, Zeiss will just pick up the PDK no matter what it is, whether it's Spectre or HSpice or ngSpice, and run with it. I'm not sure how long it's going to take other simulators to get around to the same model, but that's clearly a good model for the future.
Unfortunately, we do not have ngSpice team joining us, but they spent a little bit time to improve ngSpice compatibility with HSpice. I don't know what is status, but there was some work to provide HSpice support within ngSpice.
Yeah,
so,
I get some
for time
feedback.
being, I think we should still be using your tool and rely on your netlist converter.
Well, it's there and it's useful when it's needed, as because of the way I ended up breaking it up into two sections, one for creating the PDK and one for patching things in open PDKs. It's not a simple system or a single complete system to use. I put all the scripts that I used for creating the PDK, those are in open PDKs, but it's just a floating Python piece of code. So it's not particularly well integrated. Would be nice to do something like that.
Already now, Mehdi is suggesting meeting to discuss needs for open source tools, and I think this is the one of the question, how to make sure that we are compatible with open source tools and will be able to exchange all the file format, schematic, layout, libraries, etc.,
Yeah.
among the tools. So this
I think beyond that,
yes.
beyond that, there's a whole opportunity here, right? Like what Marcus with SemiMod are doing, or you guys are expert in modeling with AWG. You know, there's a real need of defining this loop where, you know, in foundries they usually have test structures, and each, you know, recipe or changes, they have a new model that is released, or based on the customers, they generate new models. So I think we could automate this whole thing for SkyWater 130 as first, but also for other nodes that are coming.
I think one of the things is to break out the model generation piece and make it pluggable. So, I mean, there's no reason that Zeiss should have to read a PDK to run models.
Yeah.
I mean, we at SemiMod had this idea that we could put a PDK into a Verilog A file at some point, and everybody has a Verilog A parser, hopefully.
Yeah.
But we're
I
not sure how realistic that is.
I mean, I hacked NG Spice years ago to dynamically reload the models because it sort of came up, and when you've got thousands of parameters to a model that can all be different things, and the model is really inefficient. So I thought, well, I'll do something which just recompiles the models, and everything that's constant will be taken out when I see the actual instance. So it's not hard to do that kind of thing where you just put in
Yeah,
a
I mean,
generic.
that's not the only
model.
issue with the ADMS interface, the compilation.
Yeah.
I mean,
Yeah.
also that it doesn't converge sometimes when it should converge and that it's slow.
I mean, I think there's another thing with AI where I mean, I've seen people using AI to help with convergence. So you can say, okay, I can take a model generator that's not that good if I can give it some help. So I think ADMS and AI would probably be a good enough solution for a lot of things. If you make the ADMS piece pluggable, the other people can then use that interface, then you may get something better if somebody's got a better Verilog A compiler. But having a pluggable interface makes that a possibility.
Yeah, I think adding to that is, this whole loop here requires people from modeling, EDA, like simulators and, designers. So I think it's worth, before, saying which is good and which is bad, basically getting together, like in this workshop or follow-up meetings, where through the analog working group maybe, and define these things, right, in a very neutral way.
Well, I think we need something like Accelera, but for open source. Accelera is the antithesis of what we want in a standards body. We kind of need our own standards body that says what these APIs and things are going to be, so that we can get the plug compatibility.
If we define standards in the open source community, will they be adopted by industry is the question. I mean, at some point, maybe yes, but...
Well, I mean, the IEEE is open. I mean, if everybody wants to go to the IEEE and do it there, you can, but it takes like forever. So I would say you do what Accelera does, which is do it up front at Accelera, and then you drop it into IEEE once it's sort of semi-mature.
So the good thing with open source is that there's no, we don't have to follow one thing, right? We can, things can evolve over time. So if we see that something doesn't work, that's definitely going to change over time, because we always choose the path of least resistance, right? So
yeah. But System C is one of those standards, which is an open source thing that sort of ended up somewhere in the IEEE. Once you got it working at a certain level, you can say, well, this is good enough to standardize for everybody to use. And I mean, there's a whole number of IEEE standards. People have just gone out and done it as a standard, but nobody really uses it. So,
yeah.
But it looks more official if you do that.
Sure.
Yes, maybe for next meeting, we can kind of isolate a couple of or identify certain flow with a couple of tools and see how whatever data information is going from one to another tool, what is missing, and when I talk about models, I talk about compact models. Now Verilog A is accepted language for compact model distribution. So we need tools which will enable compact model implementation into a simulator. Then if we have a model in simulator have to read or accept certain library formats. Then as long as all is at transistor level, so we can look at simple analog blocks. If from this point we are moving to digital design, probably we need to look at I don't know, timing libraries or something else which will go beyond transistor level design. So we need, and I guess
well, I think one of the changes is when we move from like something from like NG Spice to Zeiss, is we then have a C++ based simulator, and in C++ it's much easier to do object-oriented interfaces for things. and that opens up opportunities to make stuff more portable and pluggable.
I agree with that.
Right. There is also other tool, GNU-CAP, and this is alternative simulator with which supports this idea of plugins.
Yeah, I mean, I tried working with
in GNU-CAP.
Yeah, I tried working with the GNU-CAP guys way back, and they were plug-in crazy. You know, they didn't actually have working code. It's kind of fallen by the wayside.
Sometimes it's difficult to communicate with Al Davis, and he has his own very strict view on simulator.
Yeah, that was kind of the problem. I think what we have all the pieces we need. You know, particularly for mixed signal and RF type stuff and the AI, we just kind of need to be able to sort of work out how the pieces sort of fit together and in ways where you can do plug compatibility. So you should be able to use both NG, SPICE, and Zeiss, you know, pretty much in the same environments. They should have the same APIs for their modeling and dumping, you know, logs and things like that. You know, and there's you know, whoever's leading, the other guys can follow. You know,
I guess maybe it's not a right place to mention this, but this is the advantage of commercial tools. They somehow standardize data exchange format.
Not much.
So
I mean, that's one of the major problems I have, is that I'm sitting in an environment at the moment where I've got Spectre, and the guys have like used all these little Spectre sort of virtuoso features that mean that I can't chuck Spectre and use a faster simulator, because it's like they're non-standard. Only some of the stuff is standard.
They're not in their world.
I would just argue, this is Rob Main speaking, but I think generally what you see from EDA suppliers, it's really a proprietary format, and it only becomes a standard because of market dominance. I think the Liberty format for static timing is definitely an example of that.
Yeah. There's a thing where we can take the existing standards that are commercial and say, okay, you know, can we build a superset of that, and can we do it in Redis or something? I mean, I was thinking, can I replace open access with Redis? Looks similar, you know.
Yeah, the problem also with these things, open access being a good example of this, is that it's really not open, right? Because it requires you to have you either have to belong to SI2, which is not cheap. I did see the one comment there relative to the compact modeling console, which is great that they've taken that on. But again, that's not necessarily a cheap body, so to speak, for different players or entities to come in. And certainly relative to open access, right? It's not open because you have to either be a Cadence customer or a member of SI2, or most likely both.
It's slightly more subtle than that. The problem is, if you ever sign the license agreement, you then can't build your own open access thing. But the thing is, you can't really patent an API. So all the open access is like many things, is an API to a database.
Yeah, I worked for a company that tried to do that. Yeah.
Yeah, right. but the thing is, a company trying to do it and getting paid for it is different from people in open source just going building something that works. You know, particularly if they're in China or somewhere.
I used to work for Sun Microsystems and Oracle. I'm referring to the fact that Oracle filed a lawsuit against Google relative to the Java API, which didn't work out so well in their case. So anyway,
it depends whether you got somebody to sue. I mean, you got to show damage, and you got to have somebody that you can sue to stop them doing stuff. And it's like almost impossible to stop stuff that's out in the open source world. You know, and you're running into this problem at the moment with Qualcomm and was it ARM with the NUVIA processor stuff they're doing? It's like, you know, what's actually patentable in ARM's ISA? Well, the answer is nothing. You know, it's like they're just like hoping that like a lawsuit will stop people doing things. You know, so and stuff that's been around for as long as open access. You know, there's nothing patentable in there. It's just trademarks and copyrights. You know, and I don't think you can copyright an API particularly and stop people using it.
What I'm hearing, all is still not only open source, but it's really open open discussion what will be next step and how to make sure that all the tools we can create smooth how to say, design
a particular one I would like to see that you could do with Zeiss is have the simulator itself be the database for something like open access. So rather than net listing, you know, Zeiss just plugs into the Virtuoso environment or whatever with the open access API, and there's no net listing involved. And then I can do a lot of things a whole lot faster than I currently get to do them. You know,
so that's an interesting idea. I guess the abstract data model that I showed in one of my slides is kind of something that points in that direction.
Yeah.
So you know, that we haven't even decided what the format of that data file would be at this point, but basically
the point is not to have data files.
well,
the point is just
so,
to have tools that are running and have their own internal representations, which may be a file system to you. You can have a file system if you like, but you have the same API as like other people, and
so fair enough. I guess what I was trying to get at was we're trying to have a way to invoke Zeiss without reading a net list. That's basically the punchline. And I guess we've mainly been thinking about having a binary file format supporting that, but I mean, we already actually do have a restart capability, but it's a transient restart that requires you to still reparse the net list. So we'd be sort of replacing that with something that didn't require you to restart the net or reparse the net list.
Yeah, I know the guys at Analog Rails have an open access compatible database, you know, so you can probably work with them on this kind of stuff.
I've interacted with them a little bit, not recently though.
Yeah.
Anywho, yeah, that's an interesting idea.
What I can hear, it's still worth to continue discussion. We are already half an hour beyond allocated time. I hope Rob does not mind. And maybe to facilitate or continue this discussion, as Mehdi has suggested, maybe we can have yet another similar panel discussion just before Christmas. And if you have any recommendation or suggestion, maybe together with Rob, we can kind of create short list of the main point to further discuss.
Yeah, I think that makes sense, Radek. So we probably, before meeting again, we should start some, you know, something we can build up next time. And, you know, I'm pretty swamped till the 15th December or 16th. So maybe we can convene after that in a smaller committee and discuss what are the main points that we need to develop or expand, and then we can call up for a different panel.
Yes, so week of the working week 51, this was just before Christmas. If there will be a chance to meet, yes, so I will be happy to join you. Otherwise, we should make some arrangement just after New Year.
Sure.
But in the meantime, maybe Rob or together with Rob, we can collect some open questions, suggestion or recommendation just to prepare a kind of agenda to continue this discussion.
Definitely.
So I guess it's time to close our meeting today. I would like to thank Rob and all the Chip Alliance for setting up our online panel today. We got a series of interesting topics for today's discussion, having Kevin update on his Verilog or system Verilog AMS standardization. Then Eric giving update on Zeiss and support for commercial libraries and syntaxes. I really appreciate Mehdi's talk with really top level overview of open source EDA tools for IC design. This was really impressive, and we should have keep expanding this listing. Nikos has presented update on AKV 3 and the work on ngSpice implementation. And last but not least, Tim shared his experience on the library, Skywater library compatibility with ngSpice. They were of high interest. I really appreciate and would like to thank all speakers today, as well all participants who are still with us. In the peak, we were more than 30 attendees within the meeting. And now I think it's a time to close. And again, thank you very much to Rob supporting, organizing today's event, all contributors, panelists for the presentation, as well attendees who were very strong, staying with us till the very end. So thank you very much. And if there will be update, of course, we will keep the mailing list and share news about eventual panel discussion quite soon. So again, thank you very much and have a great day.
Thank you.
Take care.
Thank you. Thanks.
Bye, everyone.
Bye-bye.